Okay, so let me start. And let me start by thanking Jelani for the invitation. It's really great to be here. So in my talk, I will describe... Okay, thanks. So in my talk, I will describe some concentration inequalities for polynomials. And it's a large topic, so obviously there are many things I will not cover. And since this is a workshop on chaining, well, my plan is to first state, after some introduction, to state some relatively recent inequality for general polynomials in sub-Gaussian variables, but then just to say very briefly, without details, how you reduce this problem to multilinear forms in Gaussian variables. And this reduction doesn't involve any chaining, so I will just mention it. And then the Gaussian case was obtained by the multilinear forms by Rafał Latała, and it does involve chaining. It appears naturally when you start to do, a quite natural inductive proof. So for the rest of my talk, for most of it, I will just describe how you can use chaining to get the bound by Rafał Latała. So I would like also to stress that most of what I'm going to speak about comes from a 2006 paper by Rafał. And after this paper, there have been some other contributions to concentration inequalities for polynomials, also using chaining, but they are rooted in the work by Rafał, so I would like to stick to this basic Gaussian setting, which already shows all the difficulties and also suggests how to handle them. Okay, so let me start with some notation. I'm going to speak about sub-Gaussian variables, so you have to formalize sub-Gaussianity somehow. It can be done many ways. I chose to do it via this psi2 Orlich norm. So this is the formal definition, but if you don't like Orlich norms, you may think of this psi2 norm of the random variable x just as the sub-Gaussian coefficient in the sub-Gaussian tail decay, and infinity if there is no sub-Gaussian tail decay. So just by applying Chebyshev's inequality to this e to x square divided by a square, you will see that if it's finite, then the tail of the if the psi2 norm is finite, then the tail of the random variable x decays like this. And the reverse is also true. If we have a sub-Gaussian tail decay, then to calculate such an expectation, you can just do integration by parts using this knowledge about the tail. And you will see then this psi2 norm is a universal constant times this sub-Gaussian coefficient. And what will be important later on is that also, it can be expressed as this in terms of growth of moments, of pif moments of the random variable x. So say for p greater than 2, the moments should grow like square root of p. So this is the Gaussian rate of growth, right? And it's also equivalent up to constants. So if any of those hold, so when x indeed has a tail decay better than Gaussian, then we just say that x is sub-Gaussian. Right, and I'm going to speak about polynomials, so let's start as a warm-up with the simplest case. So just linear combinations, like linear forms in sub-Gaussian variables. And it's a very well-known classical fact, just using the moment-generating function or Laplace transform, if you wish, that if you have a sum of independent sub-Gaussian variables, and if you center it, then you will get concentration, which is governed like this, right? So it's more or less like the fact that a linear combination of Gaussians is still a Gaussian variable, and you know what the tail decay then is, right? So I'm not going to spend any time on this. So the real question is, what concentration can we get for polynomials in independent sub-Gaussian random variables? So let's move to polynomials, but still in the simplest setting. So arguably, the simplest polynomial after the linear combination or the sum is a quadratic form. And here we have this classical inequality. It's usually called the Hanson-Wright inequality, but actually they proved something slightly weaker in the 70s. And later, in different settings, this inequality was recovered independently by many people. So let's assume that we have independent mean zero now variables which are uniformly sub-Gaussian. So this L bounds the psi2 norm of all of them. And we have a matrix which defines a quadratic form in our random variables. So then we cannot hope for a sub-Gaussian tail decay for all t, because, well, we have a square, right? If you square a Gaussian, you will not have a sub-Gaussian tail decay anymore. But it turns out that for small t, you can write a sub-Gaussian inequality. And how small t you can allow depends on this matrix A. So in fact, you can think of it as having two regimes of concentration. For small t, you have some sub-Gaussian decay. Later, at infinity, you have only the sub-exponential decay. And of course, this is the right one. And the coefficients are governed by two different norms of the matrix A, defining the quadratic form. So here, this is the Hilbert-Schmidt norm and the operator norm of the matrix. And just by single bars, I will always denote the Euclidean norm of a vector. Right? So this is just the usual operator norm. OK, the simplest way to prove it, at least in the Gaussian setting, would be to diagonalize the matrix A using the rotational invariance of Gaussian random vectors. And then you just reduce it to a sum of independent random variables, which are basically those Gaussian squared. So then you have a lot of inequalities you can apply, like, I don't know, Bernstein psi-y inequality or something like that. OK. Anyway, we have two different norms here. And it turns out that in the Gaussian setting, we cannot avoid them. In some sense, this inequality can be reversed. If you change the constant here, and instead of 2, you will have like 1 over a big constant, then you can reverse this inequality. So we see that if we want to speak about general polynomials, we need some candidates for norms which would describe the coefficients. And of course, we expect that there would be many more regimes of tail decay in the general case. So how to generalize this inequality? Well, we need those counterparts of these two norms. And what turns out to be the right counterpart is, well, what is known as injective tensor product norms in functional analysis. But OK, I will just write a formula, and we will not use the fact that these are injective tensor product norms. And in fact, you may not look at the formula. It's quite ugly. Instead, in a moment, I will show you examples, and then it will become clear. Actually, you can see it here already. I put it down here for future use. So now let's consider, for example, an array of real numbers, which is indexed by d indices. Right? So it was 2 for the quadratic form. And now we will have a lot of norms. Unfortunately, the notation here is quite complicated. You need some time to get used to it. But those norms will correspond to partitions of the set from 1 to d. So d is the number of indices here. So by partition, I mean a partition into pairwise disjoint non-empty sets. And OK, this is the formula. As I said, you may not read it. These are the examples. And I hope that now it will become clear. So let's take d equal to 2, like we had in the Hanson-Wright inequality. And here in the subscript, I always write the elements of our partition. So here we have a partition into just the trivial one, just a single set of 2 elements. So we define all those norms via duality. So we look at sums over ij, coefficients of our matrix, times multiplied by some test vectors, elements of a test vector xij. And here I have only one set in the partition. So I have only one test vector. Its energy, let's say, should be at most 1. So just by Cauchy-Schwarz, you can see that this is just the Hilbert-Schmidt norm. If I have a partition into 1-element sets, so I have 2 elements in the partition, I'm going to have 2 test vectors, xi and yj. And you see, the first vector depends only on the first index. Let's say that the order of indices is ij, right? The second vector depends only on the second index. And all of them should have this second norm 1. So you can recognize here the operator norm of A, right, which appeared. So these 2 guys appeared in the Hanson-Wright inequality. And let me just show you those 3 examples, right? So for 3 indices, I put them here also. So here we have a partition into 2 sets. 1 and 2 go together. So 2 sets, so we have 2 test vectors. xij, because 1 and 2 go together, and yk depends only on the third index. Also, their squares should add up to at most 1. And we have something like that. Here we have 3 sets in the partition, each of them one element set, so we have something like that. And here for the trivial partition, for just one test vector, so this is a counterpart of the Hilbert-Schmidt norm in this setting. And then, for example, this one is a counterpart. Well, this is the norm of A seen as a linear form, right, in those variables x, y, z. So I hope that this is clear. Let me just mention that, of course, you can always get rid of one of those test vectors just by using Cauchy-Schwarz, right? But you have to keep the rest of them. OK. And I will use PD. So we have, for each partition, we have a norm. So I will use PD to denote the set of all partitions of this set. And it turns out that these norms are the thing that should appear in concentration inequalities for polynomials in sub-Gaussian variables. So let me rewrite this Hanson-Wright inequality in this new language. So when you define a polynomial just as this quadratic form and let x be the vector of our random variables, then, well, you can see that this matrix A, up to a constant, this is just the matrix of second derivatives of our polynomial. And we don't care about constants here. So in fact, the Hanson-Wright inequality can be written like that. Here, this denotes the minimum. Right? Normally, I write min, but I put it here like that to make it fit into one line. Right? So it's the sub-Gaussian decay for small t is governed by this 1, 2, well, norm of the matrix, like this is the matrix of second derivatives. And then we have the sub-exponential decay with this operator. So having this formulation, we can generalize this to arbitrary polynomials. And this was done first for polynomials in Gaussian variables by Rafał Latała, as I said, and more recently by Paweł Wolf and myself for general sub-Gaussian variables. Let me perhaps say what is a tetrahedral polynomial. It's a polynomial in which each variable in a product appears in power at most 1. So you can have something like x1z, but you cannot have, for example, x squared z, or I don't know, x3y squared, right? So basically, it's a sum of multilinear forms. OK, so this is the theorem. And unfortunately, it gets quite involved, but this is the nature of things here. So don't worry, quite soon I will move just to multilinear forms, and it will be notationally simpler. So we assume that we have independent random variables, uniformly sub-Gaussian. We have our polynomial of degree d. And then, well, its tail decay is governed by, you have to look at all the derivatives, matrices of derivatives of order from 1 to d. Of course, the derivatives of order d plus 1 just are 0, because it's of degree d. Integrate them. Here, by integration, I mean that we integrate coefficient by coefficient in our I-indexed matrix. Take all the possible partition norms, well, and take the proper power, which turns out to be 2 over the number of elements in the partition. And then, as you can see, there are many, many regimes, right, starting from the sub-Gaussian regime and ending at t to the power 2 over the degree, which corresponds to the partition into singletons. Right, so let me perhaps just say in a few words why this is a generalization of this Hanson-Wright inequality, because it looks a little bit different. It looks similar, but not exactly the same. So first of all, here I have more terms. Right? Here I have only derivatives of order 2. If I apply this to a multilinear form, and to a bilinear form, sorry, then I will have derivatives of order 2 and also derivatives of order 1. This is a consequence of the fact that here I don't assume that my variables are centered. the Hanson-Wright inequality was stated for centered variables. If you want to use it for variables which are not centered, you have to center the variables, and then an additional linear form will appear, which will give you the missing terms, which are here. And second, here I have the expected derivative. Here I don't have the expectation. This is just because for a polynomial of degree d, well, the derivatives of order d are already deterministic, right? So the expectation there doesn't change anything. It's just to write it in a shorter notation. OK, so some comments before I pass to what is, sorry? PI, it was the partitions. So the matrix of derivatives of order I has I indices, right? So we partition, let me go back. So for example, if we have the second derivatives, we can have two partitions, right? And PD was the set of all possible partitions, right? So we just partition the set from 1 to I, where I is the number of indices you have in this matrix. And we use this rather complicated formulas, right? OK, the point is that here you have just a bunch of different terms. And what is perhaps important to note is that contrary to the case of linear forms, those norms here, they do not depend on the coefficients of the matrix just via the absolute values, right? So already the operator norm, it does not depend only on the absolute value of the coefficients, but it's even not monotone in those absolute values, right? So this causes some difficulties in applications, but OK, maybe let's not discuss it in detail. So some remarks. Again, like in the Hanson-Wright inequality, if the variables are standard Gaussian, the inequality can be reversed. Again, I mean that I replace this constant 1 over CD by some other constant, and instead of 2, I have 1 over some big constant, and then you will get an inequality in the other direction. Now, this is what I mentioned at the beginning. What about the proof of this result? So it turns out that it can be deduced just from an inequality for multilinear forms, so for rather special polynomials, in Gaussian variables. But the reduction is quite tedious. Actually, I don't know of a simple way of doing it. So let me, without writing anything, because it involves no chaining, let me just say, like in 3 sentences on how you reduce it. So you write your polynomial as a sum of some homogeneous polynomials of different degrees of homogeneity and of some special form. And then, because of the special form of those homogeneous parts, using some general inequalities from probability known as decoupling inequalities due to De La Peña and Montgomery-Smith, you can replace each part by something which conditionally is a sum of independent random variables. And then you use the usual tools for sums of independent random variables, but you use them conditionally. So you symmetrize by using some additional independent Rademacher sequence. And once you symmetrize, you can use the contraction principle. So the point is that basically, whenever you have, for example, x1 to the power of 3 in your inequality, you will replace it by a product of 3 independent Gaussian variables. So you end up with a bunch of multilinear forms. You use the triangle inequality on the way. You end up with a bunch of multilinear forms in Gaussian variables. Use the result by Latawa, which I will state in a moment. Well, and then you get on your right-hand side, you get an enormous sum, which involves those partition norms. But unfortunately, those norms are not applied to the matrices of derivatives. And then you have to use some combinatorics play with those coefficients and linear algebra to show that this right-hand side can be actually bounded by quantities involving those partition norms of the derivatives. And as I said, no chaining, and I believe it's not very enlightening. It's just a lot of technical work. The Gaussian case is definitely more interesting. And it's there that chaining appears. So let me pass to that now. Let me introduce the setting here, which is slightly different than in the Hanson-Wright inequality. So I will look at multilinear forms, meaning that, for example, for degree 2, I will not look at quadratic forms, but rather at bilinear forms. So we have standard IID Gaussian variables indexed by I and j. So j ranges from 1 to d. So you may think of it that we have d standard Gaussian vectors in Rn, right? If you fix d and consider gi, where I changes from 1 to n. And we have a matrix which is d-indexed, right, to define a d-linear form. And this is the definition of the random variable we are interested in. So if you look at this random variable, right, so the difference is that previously in the Hanson-Wright we were applying the same sequence. We had only one vector. Here we have d random vectors. Maybe to make it, because I know that this notation is quite ugly. So instead of xi, xj, now we are looking xi, yj, where x and y's are independent, right? So when you write down the inequality from the previous slide, this one, in this special case, well, all those expectations of derivatives of order smaller than d will disappear, and you will have something like that. So once again, A has d indices. You look at all the partitions of the set from 1 to d. Each partition defines a norm of our matrix A. Well, and we have a bunch of terms like this. Starting from the Gaussian term, for the partition into a single set only, it will be the power t to the power 2 over 1. And for the partition into one-element sets, we will have t to the power 2 over d, which for d equals to 2 agrees with this Hanson-Wright. It's just t to the power of 1. And this is the inequality that is the previous theorem specialized to these Gaussian multilinear forms, but it turns out that everything can be reduced to this inequality. So now, for polynomials of degree greater than 2, and also actually for 2, but definitely for degree greater than 2, it's convenient to work with moments. Usually in the concentration of measure theory, people like to work with the Laplace transform. But once you go to degree 3, in Gaussian variables, the Laplace transform does not exist anymore, right? It's infinite. So you need to work with something else to get the tail decay. And it's an exercise, just like on my first slide. This psi2 norm could be expressed as in terms of the growth of moments. So here, this tail decay up to constants. Just please remember that CD may change. This CD is not the same CD as here. But up to constant, this inequality is equivalent to a growth of moments like this. Okay, so this is what we want to prove, in fact. So let me just show you the simplest case of d equal to 1. So, okay, our multilinear form is just a linear form. Of course, a linear combination of Gaussians, again, a Gaussian variable. So we know the standard deviation, and we know that the moments grow like square root of p. So this is trivial in this case. One just has to note that this corresponds to this complicated formula, right? But for d equal to 1, we have just a one-indexed matrix, right? I mean, we have one index, and we only have one partition, right? All you can do is to take this one-element set. And for higher degree, it's natural to proceed by induction. Why? Because when you condition, for example, on G2, you fix G2, you use Fubini, and you have you just reduce the degree of the polynomial by 1 if you fix G2. So for d equal to 2, it is still easy, but I want to show it to you because then I guess it will be simpler to digest the case, the general case. So this is our bilinear form, which we called zit. write the moment. We apply the previous trivial Gaussian inequality with, OK, so here it's the other way around. Sorry, we fix G1, and we apply the previous inequality to G2. OK, we raise to the power p. So we end up with something like that. And now we have, I skipped the superscript 1 because this G2 disappeared already. So these are just standard Gaussians. And I'm interested in estimating moments of this random variable. So now I'm going to do something which is not necessary in this d equal to 2 case, but it will be natural for higher d. So let me do it also here. Here, we have the sum of squares and the square root, right? So we can express it via duality by introducing this auxiliary variable x and writing things as supremum. So as you can see, already here, we end up with the need of estimating the supremum, I mean the pith moment of the supremum of a certain Gaussian process. And because of Gaussian concentration mentioned by Jelani, when you want to estimate the pith moments of a supremum of such linear combination of Gaussian variables, where the coefficients come from some set t, then in fact you reduce it immediately by Gaussian concentration to estimating the first moment. Why? Because this is the Lipschitz function. This is a Lipschitz function of GIs. And the Lipschitz norm is just the maximum L2 norm of vectors from our set capital T. So remember, if something has sub-Gaussian concentration, then the growth of moments is like square root of p times the coefficient in the sub-Gaussian concentration, like in my first slide. So from Gaussian concentration, we will have this term. And this, the first moment, comes from the fact that such variables are concentrated around the expectation, right, and not around 0. So this is just from the triangle inequality. So now let's have a look at this supremum. In our case, what is t? T is the collection of vectors whose ith coefficient can be expressed as sum over j, aij times xj. Right? So when you write the Euclidean norm of this guy, it turns out, and take the supremum over x's, it turns out that this is just the operator norm of the matrix. You perhaps need some time to pass from this notation to the usual notation. I know that it may be confusing because of this notation change, but it's in fact just the definition of this norm. And the supremum, well, in this case, if we get rid of this x to express it like we had here, and we just calculate the second moment, it turns out that this is this Hilbert-Schmidt norm. So indeed, plugging our norms here and using this moment estimate, we will get the tail decay, the moment growth like in the Hanson-Wright inequality. So as you can see here, it is quite easy. And I could have written it without this suprema, but it will not be the case for d starting from 3. So that's why I did it like that. OK, so sorry? Yes.
So this can be seen as like bilinear version of Hanson-Wright.
Yes, and
can you derive binomial version using this?
In fact, there are those decoupling inequalities I mentioned.
So
Yes. So yes. So a priori, like the version for quadratic forms is more general because each bilinear form can be written as a quadratic form. You just make the matrix bigger, right? But due to this decoupling inequalities, it's in fact equivalent. OK, so let's try to repeat this argument for d equal to 3. And don't worry, I'm not going to d equal to 4. It will be notationally already quite involved here. But the beginning is quite easy. So our random variable we are interested in is just a trilinear form. And let's apply the Hanson-Wright inequality for d equal to 2 to G1 and G2, treating G3k as fixed, just use foo-beam. OK, so what did we have there? We had the 1-2 norm, where 1 and 2 go together, and this norm when they go separately. But now, the matrix of coefficients is random. It depends on this GK3. Well, again, I skip the superscript 3 here. So what we end up with is the need to estimate the moments of those partition norms of some random matrices. And those random matrices are obtained by, say, linear combinations of matrices, deterministic matrices, with Gaussian coefficients. So let me denote this partition norm, this random variable by x, and this one by y. So the first term, estimating this expectation of x to the power p, is easy. Because x, this partition norm, 1, 2, by definition, it was such a supremum. Well, before, OK, in the definition, it doesn't matter if I have absolute values or not, because we take it over the ball, right? But here I didn't put them. OK, so this is just by the definition. And again, by the concentration, because it is, again, a supremum of some canonical Gaussian process over, well, here over some Euclidean ball. So again, I can bound the pth moment by the second moment plus square root of p times the Lipschitz constant. But when you calculate the Lipschitz constant now, we'll get such an expression. And when you express this summation over k of squares and the square root by introducing another test vector, let me just go, oh, it's here, right? You will see that this Lipschitz constant is exactly this partition norm corresponding to partition into two sets. So you can see that those injective tensor product norms appear quite naturally when you want to do the induction. They just pop up here. Now, what about the second moment of this x? Well, so just we have a supremum over the ball, just use Cauchy-Schwarz, and calculate the second moment. It turns out that this is this partition norm corresponding to a partition to a singleton, this counterpart of this Hilbert-Schmidt norm. And indeed, please note, when we plug them here in front of this guy, we will have the power, after taking the p root, p to the power 1 over 2. So this is the number of elements in the partition divided by 2. In front of this guy, we will have square root of p coming from here, but another square root of p coming from here. So it will be p to the power 1. And this 1 is, again, the number of elements in the partition divided by 2. So it agrees with the formulation of the inequality. And this term is easy. So what about the other term, right, which we have here, p to the power p? And now the problems start because we don't have a single test vector, but we have two test vectors, right? So now we are looking at operator norms of random matrices. So the concentration part works. When you express the Lipschitz constant of such a function with respect to gk's, it will be this. Again, introducing this additional test vector, we can write it as this partition norm. And before, we had p to the power 1 in front of it, after taking the p root. Now introduce an additional square root of p. So we'll have p to the power 3/2, which is exactly the number of elements in the partition divided by 2, as it should be. So what we are left with is the expectation of this guy. And here you can see that we have an expectation of some stochastic process indexed by the Cartesian product of two Euclidean balls. So this is where chaining or chaining-like ideas, to be more precise, come in naturally. So for higher D, there are similar difficulties, but it gets more complicated, more terms appear, and well, it wouldn't be a good idea to do it for general D, because anyway, if you understand the case of D equal to 3, you can, with some effort, write down the general case. Well, you need to understand this case first. No, so there are more terms that appear, so which you have to take care of, but they are, after some change of notation, in a sense, they are of a similar nature. So it does get more involved also at the technical level, but the main ideas are the same. But okay, notation is one of the obstacles, right? Because it becomes really very involved. When you go to the paper by Rafał Latała, it's written already for general D, and then to understand it, I guess you have to do the D equal to 3 case anyway, because otherwise it is very difficult to follow. So what inequality do we need? So to have the right powers of P, please remember that we had P to the power 1 in front of this expectation. And we want to replace it by some quantity involving those norms. So if we introduce this norm, we can allow only P to the power 1/2 in front of it. So it has to be divided by square root of P, right, to reduce the power. These norms, well, the power of P in front of them should be 1. So they appear here without any P in front of them. And if you want to introduce this norm, which is the smallest of them, you have some freedom. You can increase the power of P by square root of P. So this, of course, I could optimize in P this inequality and prove it in such a version. But to do the induction, we need this formulation. And in fact, this is the formulation which appears in the proof. So I will not do this optimization in P. And here we have the supremum over the product of Euclidean balls. So for the argument, it will be more convenient to consider general sets T contained in this product. So the argument will be a little bit like chaining, but it's not exactly the chaining that appears in the formulation by Talagrand. And in fact, I'm not sure if in general this formulation of a chaining argument, if it's equivalent to this gamma 2 functional. I don't know. But the idea will be rather to, when you have your set T, it's also a tree-like idea, to replace this set T by some T1, let's say T2, T3, simpler sets. And well, in a sense, you don't approximate, I will show you the details in a moment, you don't approximate the points here, but you chop the sets. At the formal level, it looks very similar, but it is somewhat different. So let me pass to it. So this is the quantity we want to estimate. And assume now that we have a nice representation of T. So assume that T is a union of some sets Tm, which are shifted by elements from the set T. Those sets Tm are also in this Cartesian product. And, well, our hope is that those sets Tm are somehow simpler than the original set T. And we would like to replace f of t by maximum of f of Tm, but we will have to pay some cost. And we want to control the cost which we pay, and then proceed iteratively by replacing Tm's, but by even simpler sets. OK, so if I have such a representation, so I can write this supremum over T just as the maximum of suprema over those sets, shifted sets Tm. Now, taking any x prime, y prime, since we don't have x prime, y prime in the supremum, I can subtract it, right? Because the expectation of our variables, if you don't take the supremum, is 0. So I can write it down like this, equivalently. And now I use the concentration. So each of these suprema is concentrated, and then there are capital N of them. So like in Jelany's talk, since they are concentrated at the sub-Gaussian rate, I can move this expectation of maximum, this maximum I can move in front of the expectation at the cost of paying the square root of log n, when n was the number of sets, times the Lipschitz constant. What is the Lipschitz constant? Well, this is just the diameter. The best you can do here is just taking the diameter of the set T in such a metric. So this is what you get first. But now I told you that the hope is that those sets Tm are simpler than T. And here we don't have Tm yet. We have this shifted Tm. So when you look at the difference between, like, what was f of t, it was in terms of the random variables in question, in terms of x, y, were depending in a bilinear fashion. So when you just plug in this bm, cm plus xy here, you expand this bilinear form one term will be, after taking the supremum f of tm, one term will be just 0 because the term involving just b and c will vanish after expectation, and we will get some mixed terms. And now, because we assumed that tm were still in this Euclidean product, we'll just do a simple thing. We will just take the supremum, just use the Cauchy-Schwarz, right? Because the x's here are from the unit ball. And now just go with the expectation inside the square root and write something like that. So it turns out that if you have such a decomposition, you can replace t by maximum of the next generation sets plus two quantities related to the original set t. So when you are given your set t, well, these quantities come with it. You cannot do anything about them. They are just given. But you may hope to partition everything in such a way that at the next generation, these coefficients of the next family of sets will be already controlled, so that you do it iteratively. At each step, you control the price you have to pay by passing from Tm to the sets of next generation in such a tree. So there are three things we have to control in doing such partitions. The cardinality of the partition. In fact, it doesn't have to be a partition, right? We just use this representation. But the cardinality of it, and these two quantities, this diameter and this, well, you can say that it's some outer radius in some Euclidean norm. So this is the basic lemma by Rafał Latała. And it tells you something. There are some technical assumptions, like I will not discuss them in detail. It's just to be able to use the induction. You need t minus t to not just t to be contained in this Cartesian product by t minus t as well, but it's just technical. For each L, we can get a decomposition like that, where you control the number of terms in the decomposition, and you control these parameters SA and delta A by this Hilbert-Schmidt-like norm of the matrix A divided by some quantities. As you can see, this becomes much smaller for delta A. And here you assume that the sets T are finite. Of course, you can assume both that T minus T is contained in this Cartesian product and that T is finite, simply because, well, by homogeneity, you can assume that you can pass to 1/2 of this, the rescaled Cartesian product. And then by separability, you can pass to a countable set and then to a finite set. So this is not a big problem. And now, when you are dealing with finite sets, the point is that at each step, you decrease the cardinality of your set. So when you do this tree, at some point, you will end. And you can do this decomposition if T has at least 2 elements. But when in your tree, when you get to a 1-element set, then f of t is just 0 because your variables are centered, right? So the important thing is that here at each step, we have the maximum of the suprema of processes for the next generation set. We don't have the sum. So that's why at each step, you just pay this price, these 2 elements. Okay, so this is what you do. Here, I don't pay attention to this constant c. So you take an arbitrary set T, and it's contained in this Cartesian product. When you look at this SA of T, right? When you express this ik, summation over ik, just by duality, by introducing some test vectors xik, you will recover this partition norm corresponding to partition into 2 elements. So in fact, this quantity is bounded by the sum of these 2 partition norms. When you look at this delta A of T, it was here. Well, here we have the diameter. When you use the triangle inequality, use the fact that x and y are from the Euclidean sphere, and express k, the summation over k of the squares, by duality, we will get the partition norm corresponding to the partition into 1-element sets. So at the first step, the price you pay is something like that. Here we had the possibility of choosing L arbitrarily. So you just apply the partition from the lemma with L equal to 1. This is the price you pay. And then you iterate. And you apply with L equal to 2, L equal to 3, and so on. So I skip the constants here, but the point is that here it turns out that we control those guys, partitions into 2 or 3 elements, appear only, this is quite surprising, at the first step. Later on, in our lemma, we control those coefficients, I mean, those characteristics of the set, only in terms of this Hilbert-Schmidt-like norm. And at each step, this is done in such a way that each step, you will have this Hilbert-Schmidt norm multiplied by something smaller, which decreases geometrically. And moreover, since we have this greater power here, the cost you pay from this log n here is compensated by the constant in front of this partition norm. And you end up with, well, this Hilbert-Schmidt-like norm times, 1 over square root of p times a geometric series. So in the end, you get the estimate that you need. So it looks like chaining, but it's not exactly the usual argument. Moreover, at some point in the usual argument, like Jelani presented it for Gaussian variables, but what you just need is that the differences are sub-Gaussian. And here at some point you use the Gaussian concentration inequality, which does not hold for general sub-Gaussian variables. And well, it's not clear to me if, in general, this procedure gives something comparable with the gamma-2 functional. We know, of course, that the gamma-2 functional bounds the quantity here from below because it is optimal. OK, so I still have like 13 minutes, so let's go back to this lemma, and let's discuss the proof of it. So as I said, I will not pay attention to these technical properties. I will just focus on the cardinality of sets and these 2 diameter bounds. So we will do it. We will prove it in 2 steps. First, we will take care of this property 4. We want this SA of Tm to be small. And then we will do another partitioning to get the property 3. So what was 4? SA of a set S was something like that. So when you look at this quantity under the supremum, this is some sort of a norm of the point xy. Right? Just, well, this is a norm. That's it. I denote it by these triple bars. So in fact, we want to get a decomposition like this, where each of the sets Tm has elements in it, have small norm. Well, the maximum norm of elements from Tm is small. So here we have a shift. So in fact, it corresponds to finding a partition with small diameter in the metric corresponding to this norm. So this is the classical topic, right, in probability on geometry, to find a good covering with sets with small diameter in terms of some norm, prescribed norm. So this is the norm. And we want to partition the set T into that many sets with diameter of this size. And what we see here is the dual Sudakov minoration. This was proved by Alan Pajor and Nicole Tomczak-Jägerman in the 80s. It actually implies the Sudakov minoration mentioned by Jelani. This is what Vitek mentioned in the previous talk as a comment. So in the Sudakov minoration, you have some indexing set T, and you partition it, you cover it with the metric, with the Euclidean metric, right, with Euclidean balls. Here in this dual Sudakov minoration, you have the Euclidean ball, and you partition it in terms of some norm. And what appears is the expectation of this norm applied to a standard Gaussian vector. So in this sense, it is a dual thing. So this is the theorem. It's not the original statement. It's the statement rewritten in a form convenient for us for the application here. So if we have a set T in the Euclidean ball. Please note that our set T is contained, it has more dimensions, but it is contained in a multiple of this Euclidean ball, just by square root of 2, so independent on the dimension, so it doesn't matter. So if we have T in the Euclidean ball, and some norm, this is the norm with which we want to cover with sets with small diameter with respect to this norm, then for each epsilon, we can cover by this many sets. This is like the original Sudakov minoration, and the diameter is given by epsilon times the expectation of this norm applied to the Gaussian. So in our case, we have 2n instead of n, but this is not an issue. What is our epsilon? When you look here or when you look here, right, you see that you should choose epsilon of this size. And when you calculate this expectation, what do you get? Well, instead of y and x, you plug in the Gaussian variables. Well, it should be one Gaussian vector here, another Gaussian vector here, but it doesn't matter because I take expectation anyway. And when you, again, you go with the expectation inside the square root, you calculate the variance here, you will get this Hilbert-Schmidt-like norm. So this gives you the partition which you want. Then we just have to assume that those sets, right, we want to decrease, we want to have a partition into at least 2 sets and decrease the cardinality of the initial set. So you can do it by partitioning somehow artificially if, for example, the original set already had small diameter, right? And then you just, from each set Si, or Sm, sorry, you just pick up one element and you shift. And then you are done like this with this first property, fourth property here. Okay, but so far we've taken care only about this SA. We still have this delta A of Tn. So we need our sets, we have to modify this T tilde m to Tn in such a way that the diameter with respect to such metric is small. And this is very similar to the proof of the dual Sudakov minoration. So how you prove this dual Sudakov minoration, at least one of the proofs, follows by looking at a ball around each point in the Euclidean ball, and looking at a certain Gaussian measure of this ball, and having a bound from below on this ball. Then looking for an epsilon net is more or less like looking for a maximum epsilon separated set. If you have a separated set, balls around points in this set are disjoint, and since we have a lower bound on the measure, and the total measure is at most 1 because you are looking at a Gaussian measure, then a lower bound on a ball at each point, on a measure of a ball at each point, will give you an upper bound on the cardinality of the maximum epsilon separated set. So here we do the same, but you have to somehow tensorize it. Because when you think about it, what is our metric here? It comes from a norm, but the norm is not on the Cartesian product, but on a tensor product, right? Because here it's a norm on matrices. So this is the general theorem. You have some norm on the tensor product of 2 Euclidean spaces, which you identify with the space of matrices, right, via this equality. And you define the metric on R2n by this formula, right? Between xy and x prime, y prime, by looking at the distance with respect to this norm of Rn squared between the tensors. So you can see that this is exactly what happens here, and the norm is like this. This is the norm on the set of matrices xij. And then it turns out that, again, you can get a lower bound on some Gaussian measures using somehow the ideas from the proof of the lower bounds for the usual Sudakov minoration, and get the following partitioning, which is, well, it is more complicated. So you partition into the same number of sets as before, but you have more complicated bound on the diameter. So here we have a better, before it was epsilon, now we have epsilon squared, it improves. And we look at the expected value of something like that. You just take the norm and apply it to such a tensor product where Gn and Gn prime are independent standard Gaussian vector in Rn. So you have two of them now. And here you have just one Gaussian vector, but you take the supremum over x and over y. Fortunately, what makes things work is that the supremum is outside the expectation now. This is important. So this is our norm. And when you apply the lemma, well, again, when you look at the cardinality you want to have, you see that you have to apply this with epsilon of this size. And you get the diameter. Well, we want it to be this Hilbert-Schmidt-like norm multiplied by this. I will get 3 in front of it. It doesn't matter. You can pass from L to L plus 1 and kill this 3, so it will be just more convenient. So what this Sudakov-like theorem by Latawa gives you, this lemma, is a quantity like this. So let's see how it behaves. When you take, the norm is this one. When you take supremum over xy in Tm, so this depends only on the projection of t tilde m onto the first n coordinates, and you look at something like that. Well, you can just, again, you use Helder and just bound the second moment of this guy. And in the end, by calculating the expectation inside, you will have the summation over Gj. And the summation over I will stay inside with squares. So this turns out to be bounded by this SA parameter of the set. And we already assumed that this SA of t tilde m was small. This is what we did at the first step. So we get 2 to minus L times 1 over square root of P here. You get another one from here. Altogether, you get the right power. The second term is similar. What about the last term? Here already you have the right power. What you need is to estimate this expectation by this Hilbert-Schmidt-like norm. Well, but this is again just Helder's inequality. Right? When you calculate the expectation of a quadratic or a bilinear form in Gaussian variables, this is what you are going to get, the sum of squares of the coefficients. And altogether, when you combine all of it, you will get this. So at first step, we partitioned into some n1 sets. At the second step, each of those sets after the shift was partitioned into n2 sets. So altogether, there are this many sets. Here, fortunately, it involves just a change of the constant in the exponent. And you just relabel all those sets, right? In the lemma, they were TMs. And this is the end of the proof of the lemma and the end of the proof of the whole theorem for d equal to 3. So let me, in the last minutes, let me just mention some further developments. So I told you that these inequalities in the Gaussian case could be reversed. Also, this result of Paweł Wolf and myself showed that they worked for general polynomials in the sub-Gaussian case. But for the general sub-Gaussian tails, they are not optimal anymore. I mean, they are optimal in the sense that they are optimal for Gaussians. But when you look at Rademachers, for example, you expect concentration for Rademachers to be better than concentration for Gaussians. And with our inequality, you get the same concentration for Rademachers and for Gaussians. So there is interest in improving two-sided bounds depending on the distribution of your random variables. And things become easier when you are looking at non-negative random variables. The class of random variables that can be handled is random variables with log concave tails. So when you take the logarithm of the tail, it is concave. So the extreme one is like the exponential variable. This is the heaviest tail that you can allow. And this was done for general multilinear forms by Rafał Latawa and Rafał Łuchowski. And recently it was generalized. This is a geometric-like assumption on the tails. This is a weaker assumption, including, for example, heavier random variables with tails heavier than exponential. This was done by another Rafał. This is Rafał Latawa, Rafał Łuchowski, and Rafał Meller recently, like 2 months ago. This is for non-negative random variables. And the case of symmetric random variables, which are interesting, for example, because you have Rademachers there, turns out to be more difficult. So for sums, it was done like two-sided bounds for d equal to 1. It was done by Gluskin and Kvapin. D equal to 2 by Rafał Latawa. And for d equal to 3, we have a paper with Rafał. So it works, for example, for Rademachers. And except for exponential symmetric variables, we have no idea how to push it through to higher d, things become too complicated. So in this case of d equal to 3, we could somehow work with refinements of those idea I showed you for the Gaussian case and get two-sided bounds, but we don't know how to do it greater generality. For tails heavier than exponential, with log-convex tails, so this function should be convex and not, it's like e2 minus square root of x, the tail, for example. For sums, it was done by these three people, and Kolesko and Rafała did it for multilinear forms. Let me also mention that there are counterparts for what is known as statistics, if you are interested in it, but I don't go into details, and that under some, oh, sorry, I'm too late. So let me just say that under some analytic assumptions, like functional type inequalities, you can get more with a simpler proof. So you assume more and you get more with a simple proof. You don't need to consider polynomials. You just assume that derivatives of, for example, order 4 or 5 are bounded. And then you get a similar bound. But this is a completely different story. So let me just mention one thing. All the inequalities I spoke about were quite sharp for fixed degree. But the constant depended on the degree, and they were really terrible. So there is a different idea, like for different applications. So there are inequalities by Kim Wu and more recently by Shudy-Sfiridienko. So they work better, for example, in random graph settings. If you want to look at concentration for the number of cycles of length 4 in your random graph, the inequalities I presented work better than those by Kim Wu. But if you want to look at cycles of length depending on the size of the graph, then the polynomial you have to deal with, the degree increases with n, with the size of the graph, and these inequalities don't give anything meaningful, whereas those inequalities by Kim Wu do something meaningful. So just to finish, 3 open problems. So from the computer science perspective, probably this one is the most important, 0, 1 valued variables to get two-sided moment estimates, because they appear in random graphs, right? Then from the probability in Banach spaces perspective, this is probably Rademacher's. And more generally, you may look at polynomials with coefficients in a Banach space. The Hilbert space case follows formally by a trick from this result by Latała, but it would be nice to have, for example, at least good inequalities for quadratic forms with matrix-valued coefficients. But there are some inequalities, but not as precise as those inequalities we know in the real case. OK, so let me stop here. Sorry for taking more time. Thank you.
Sorry, on your last point, is anything known about concentration of quadratics when the coefficients belong to a set in Rn, for example?
Well, in general, OK, I should have mentioned it, actually. There are inequalities which are even two-sided for Gaussian variables, but they are expressed, the coefficients there are expressed in terms of expectation of suprema of some processes. So these are inequalities due to Borel and independently Arcones and Ginet. So for example, the quantities you have to deal with are like expectation. Let's imagine that we are looking at supremum over A in some set A of some Aij, Gi, Gj, right? So then you will have supremum over A, for example, supremum over X in B2n, of something like that. And this is the coefficient that enters the tail inequality. And well, this is just a number, right? But to estimate this number, in general, it will be difficult, right? So a lot of work that we did here was to estimate such things for some special sets, for A being, for example, so what we did for d equal to 2 was when A was a singleton, right? And it becomes more complicated with D. So there are inequalities, but it's rather difficult to apply them, although there are some applications in statistics where you can bound those suprema by using some Slepian lemma or something. Okay, questions? So thanks a lot.